Hi, everyone. Welcome to our fifth lecture of DSCI 572. So, in the previous lecture, I've introduced you to the idea of computing derivatives in an efficient manner. And we talked about automatic differentiation a little bit. And then I showed you how we can train neural networks using the PyTorch framework. And I've also recorded a complement video for you explaining the intuitions behind neural networks and why they're so good in modeling complex data. So, has everybody watched the video? Yeah, okay, it seems so. Okay. So before moving on, please do a git pull on the course repo because I've changed the data set. I've increased the number of samples that we have for the image data, Bitmoji data, and I've also made a number of updates to the lecture notes. Okay, so today we're going to be talking about the details of how gradients of the loss function are computed in a neural network. In the last session, I only glossed over how these derivatives are computed using automatic differentiation, but I didn't walk you through the details of it in a neural network. Okay. All right, so last time we discussed that essentially when we want to do any optimization on the loss function using gradient descent or any of its variants, we need the gradients in order to adjust the parameters and hopefully find the minimum of the loss function. So for computing the derivative, there are a couple of approaches that I've told you about. We can do symbolic differentiation, the pen and paper type of computation, working out the derivatives yourself and then coding it inside of Python, which is obviously not at all efficient for large complex models, especially in case of neural networks. This is impractical. The other approach was numerical differentiation, and that's when we use the definition of a derivative, and then we perturb the values of the x's, for example, or the parameters by a small amount, and then we f of x plus h minus f of x, like this term that you can see here, divided by h. That gives us an approximation to the derivative. However, this is just an approximation. And the other thing is that it is very, very inefficient to compute gradients in this way because we have to do as many function evaluations as we have input dimensions for our model. Okay, and finally, I told you about automatic differentiation. And the core idea of automatic differentiation was that if we don't need the analytical form of the gradients, which in training neural networks, we don't need the analytical form, we're only interested in the values, then we can decompose the entire function that we're working with into smaller elementary or primitive little functions, and then take the entire loss function as the combination or composition of these tiny elementary computations. And in that way, if we do that, the thing that happens is that we can use the chain rule from calculus. And we can you can track the computations along the way, and then we can compute the derivatives using the chain rule. And in this lecture, I'm going to walk you through the details of that. Okay. Questions before moving on? All right. So this is the structure of a very simple neural network with only two hidden neurons. So anything between the input layer and the output layer is called a hidden layer. And here we can see that there is a weight and a bias associated with each neuron. And then we multiply the input by the weight, we add the bias to that, and then we pass everything through an activation function. And then this is one layer. If we had other layers, then the process is essentially the same. Again, we receive inputs from the previous layer, multiply by weight, add a bias, pass-through activation functions, and so on. So we do this in every layer. Okay, can someone remind us what was the intuition behind using activation functions? So if you watched the video, you should know this. Sure. The activation function is there to introduce some nonlinearities, but how is it that this nonlinearity actually helps us in modeling nonlinear patterns? Yes? Exactly. Exactly. So the core idea of adding activation functions is that an activation function is basically a transition between two states. So it's just like a step function. By combinations of these step functions, we can make little bumps. And you can imagine whatever function we have, however complex it is, if we have enough number of bumps, we can basically approximate that function as best as we want. So at least theoretically, we can do that. So that's the intuition behind doing this. Basically, each neuron, together with its activation function, gives us the control over designing a bump or a step for us in the region that we're interested in. And then we combine all of them together, or we learn how to combine them together by using an optimization algorithm in the best way possible in order to approximate our function. So that's the intuition. All right, questions? Yes?
Do we essentially add these sort of activation functions whenever we have some sort of classification problem, or we also add them to regression problems?
Great question. So do we use these activation functions only when we're dealing with a classification problem, or even when we're dealing with regression problems? So the interesting thing is that you're seeing this sigmoid, and that's what probably has made you think that, okay, this might be a classification problem only. So the thing is, no, even with regression problems, the activation function still does the job of doing micro-classifications. So around each point in a regression problem, we can imagine that, okay, for example, if we have a line, so between one point and the other point, then we can think of the job of a neuron to basically classify the inputs between the first point and the second point. So we can think of a regression problem as many small, tiny, little classification problems. So that's kind of the idea behind using these activation functions and its relation to a classification problem. So what really determines what we do in terms of whether the problem is a classification one, a regression one, happens at the end layer. So in a regression problem, we have the MSE loss. In the classification problem, we have a cross-entropy loss. That's what it decides it. But intuitively, this is why we have activation functions. Okay. All right. So this is our loss function, and then we will have a vector of gradients with respect to the parameters of the problem, and this is what we're interested in computing using automatic differentiation. So let's see how that works. Okay, consider this example of a neural network. I have given you example values for the weights and biases on this network, and I will also give you sample inputs for the x values, and then we'll see how the computation of the gradients works. Okay, so for the input, we use these two values, 1 and 3, for x1 or x2. For x and y, we use 1 and 3, so x is 1, and the output is 3. And then what we do in the first step is that we do what's called a forward pass, meaning that we feed the network, or we feed the model with the input value x, and we pass it through the network. So we start from the input layer, okay, x goes into the network, is multiplied by w1, and then it's going to be added to the bias B1, passed through the sigmoid, again multiplied by W3. Okay, that's the upper branch. And then for the lower branch, again, we do the same thing. Multiply by the weight at the bias, pass through activation, multiply by the weight, and then finally sum everything up. So this process is called forward pass in the network. And in PyTorch, this is defined using the forward method inside of our class. So that's what tells PyTorch how to forward that input through the network. Because you might think, okay, in this network, this is the only possible way of forwarding the information. But in more complex networks, there are a multitude of ways to pass the information, and it depends what you want to do in that case. Okay, so basically, the idea is that passing of information is not always happening in a sequential manner. Sometimes you have other branches, other connections that are specialized to do other things. Okay. All right, so this is basically the forward pass step. You can see X and Y, and those are the results of the computations along the way. Okay, so you can see that at the end, I have computed a prediction for Y, and then I'm using that prediction in the loss function to compute the loss value. Okay, so one forward pass results in the computation of the loss value. Okay. Now, let's see how we can compute the derivatives of the loss function with respect to the model parameters. So let's start from the last node, the output node over here. Okay, and let's have a look at this. So we have the loss function over there. This is the predicted value, y hat. Okay. And then, if we want to compute the derivative of the loss function or the gradient of the loss function with respect to any of these intermediate variables, the weights and the biases along the way, we can use the chain rule, basically. So for example, if you take partial L to partial W4, meaning the gradient of the loss function with respect to W4, this is how it's computed. So we don't know what the gradient is just directly. We have to go step by step. So we say, okay, partial L to its intermediate variable. So partial L to partial y hat, and then y hat then is related to W4, as you can see in this green expression here. Okay, W4 exists here, so we take partial L to partial y hat, then partial y hat to partial W4. And that's how we can compute the gradient of the loss function with respect to that particular parameter. So right here you can see the application of the chain rule. Okay, so that's one. For W3, works in the same way. Partial L to partial y hat, then partial y hat to partial W3. Okay, this is because the value of the loss function is not directly connected or related to W3 or W4. There are intermediate computations happening. And whenever that's the case, we can use the chain rule. You take your derivative with respect to what variable you have, and then the derivative of this variable that you have with respect to the target. Okay. And also, you can see that we do basically the same thing with the bias. So partial L to partial B3. Again, the gradient of the loss function with respect to the bias there. Partial L to partial y hat, because it's indirectly related to B3, and then partial y hat to partial B3. Okay, so you can see that right at this stage here, we have been able to compute the gradients of the loss function with respect to the parameters of the model. So B3, W3, W4, these are unknown, and the values that you see right now, these are just random initializations. Okay? So we don't know the value of those, and the objective of this training procedure is to find the best values that minimize the loss function. So this is how we do it. Okay, so at this stage, we have successfully computed the derivatives or gradients of the loss with respect to those parameters of our model. Questions about this?
So when we define the weights and the bias, they have to be tensors as well, right? So
Yes.
in that case, we have
Yes, that's right. Sure. So just like we discussed in gradient descent, stochastic gradient descent, the choice of where you start your optimization algorithm in terms of the parameters of the model. So you randomly initialize them, you start from a point, you do your gradient descent from there. The other thing is that how you choose your x's and y's, so the batch that you're choosing, which data points you choose. So absolutely, that does affect it, but the hope is that even if you start from different points, you're going to converge on the same minimum value. But potentially, yes, there is the risk of basically getting lost in the loss surface and not finding the minimum value because you start from a point that's not good enough. Other questions? Okay. All right, so this is one stage of our computations. Now, this is the results of our computations. So, partial L, the gradient of the loss with respect to all of the parameters, have been computed for this unit or for this neuron. I'm not going to call it a neuron because we don't have activations or anything after that. So for this computational unit, we have everything. All right. So how can we compute the other gradients, gradient of the loss function with respect to the other parameters in the network? Because we had a bunch of others, like W1, W2, B1, B2. How do we do that? So the process is exactly the same. Okay, so we have the results from our previous step over here. Okay, and then how can we compute the value of the loss function with respect, for example, to B2 here? So we can see that the loss function is not directly related to B2. It doesn't directly contain B2, so we have to use the chain rule because it's indirectly related. So what we can do is that, okay, we can take the first step, partial L to partial y hat. That's the first step. Then partial y hat to partial A2, second step. Then partial A2 to partial Z2, that's the third step. Then partial Z2 to partial B2. Okay, so a bunch of intermediate steps because in each of these steps, the value that we're focusing on only has access to its own variables. So for example, partial L only has access to partial y hat. The loss function L only has access to y hat. Y hat only has access to, in this case, to A2, for example. And A2 only has access to Z2 because this is how we compute that. And Z2, then it's Z2 which has access to B2. This is why we have to use the chain rule. Okay, so similar thing for B1. Again, same set of computations. We can't directly compute the gradient of loss with respect to B1, so we go step by step. Partial L, partial y hat, then partial y hat to partial A1 to partial Z1, then finally partial Z1 to partial B1. Okay, and what's important here, you can see that along the way, in order to compute the gradients with respect to these biases or the weights, I need the values of the gradients from the previous step, right? For example, here, when I say partial L to partial y hat and partial, this value itself, I have computed already at this stage. So partial L to partial y hat. So I have that value. I have already computed. I can use that. And then when you do the same thing for the weights here, then you're going to use partial L to partial W3, partial L to partial W4, and so on and so forth. So this is why we have to start from the output and then make our way back to the inputs. Because it's only at the end step, at the final stage, that we can compute everything. If you start from the first stage here, from the inputs, then if you want to compute partial L to partial W2, you can't do that. Because you have to see, okay, how is W2 related to the next variable, and then how is the next variable Z2 is related to the next one, and how is the next one related to the next one. So, does this seem like something that we have previously discussed in another course? Does this remind you of any particular? Exactly. It's like recursion. So you have to hit the base case, which in this case is the partial L to partial y hat. That's the base case where we can directly obtain some numerical values, and then we work our way back up. Like in the recursion tree, we had to go down the tree to the endpoint, to the base case, and then go back and compute all of the values that were pending. So this is indeed a recursive algorithm in its own sense. Questions? Yeah, this one. Yes. Okay. Okay, let's see. So we have partial N to partial, okay, and then, yeah, partial A2 to partial Z2. Maybe we have computed it somewhere else. So here? This one. Yes, that's right. That's going to give us W4. Yeah. Okay, yeah. Yeah. Yeah, so it's coming from the previous step. Okay, so here. Mm-hmm. That's right. But okay. But partial A2 to partial Z2. I don't see it. So yeah, it should be a little bit more involved. Yeah, I have to work out the derivative myself. So basically, yeah, you just have to take the derivative of this expression with respect to this variable. It should be correct. Z2 with respect to B2, that's correct. Okay, yeah, we can work this out later. Okay. Yeah, but I have checked the computations. They are correct. Okay. Well. So this is the summary of the computations that we have done, and just like I showed you, using the chain rule, I have computed everything that we have here, the partial derivatives of the loss function with respect to the unknown parameters of the model, the weights and the biases. So we have everything. Okay, I haven't shown all the steps for all of the variables, but I have shown the required steps for B1, B2, and the rest is basically the same. You just take the derivatives. Okay, so to summarize the process, as we have seen, we do one forward pass, and that's to get from x to the values of the loss function, compute a loss value. And then, as you have seen, we do another backward pass. So we go from the outputs backward towards the inputs in order to compute the gradients. And we start from the last node because that's kind of our base case. That's what we can compute directly. And then we work our way back to the inputs. Okay, so one forward pass and then one backward pass. Right. So this process, when applied to neural networks, this process of differentiation is called a backpropagation algorithm. So basically, to be exact, when you apply automatic differentiation in reverse mode, we also have a forward mode automatic differentiation, which we won't discuss because they're not used in neural networks. When you apply that in the context of neural networks, meaning that you use that automatic differentiation to compute the gradients of the loss function with respect to the weights and biases, then this entire algorithm is called the backpropagation algorithm. So you basically propagate the information that you obtain from the gradient of the loss function through the network in order to compute the gradients with respect to all of the parameters in the model. Sometimes people interchangeably use automatic differentiation with backpropagation. They take them to be the same thing. So it's really the boundary between the two is really blurry these days. So you might see the word backpropagation used to mean automatic differentiation, but know that the more precise definition is that backpropagation is the application of automatic differentiation in the context of neural networks. Okay. All right. Before moving on to the next question, to the next part, are there any? Yes.
Yeah, so for calculating something not like sigmoid, for example, like a ReLU function which is not differentiable at one point, is there a way to know that?
Mm-hmm. So, okay. I was going to discuss other activation functions in the next part, but it was thought for a long time that we definitely had to use activation functions that were differentiable at any point. And then people started, for a problem that I'm going to discuss in the next section, for some problems, people started using other activation functions that were, their derivative was discontinuous. And then they saw that it was working very well, much better than other activation functions. So although technically in mathematical terms, you might not be always able to prove theorems about functions that are not differentiable, but in practice, they work just fine. For ReLU itself, I think we have theorems proven so that the discontinuity in the derivative is not a problem, but for other functions, yes, mathematically there could be problems, but practically seems like it's working. Yeah. Okay, other questions? All right. So PyTorch, in the PyTorch framework, we have a package or module called AutoGrad, which takes care of doing this automatic differentiation that we talked about in a very efficient manner, just as we saw. So if we go ahead and let me see. So let me show you how it works in action. So I have created the same neural network as you see on the diagram using PyTorch here. So we have a linear layer here. That's the hidden layer over here. And then we have the output layer over here. Okay, those are the two linear bits that we have to define. And then what we do, we start forwarding X through the network. So the first thing is that we pass X through the hidden layer, okay, and then save the results back in X. And then this time we have the sigmoids. Then we pass the X's, the results, through the sigmoid function, and then save the results back to X. And then finally we pass the results through the output node over here. Okay. All right. And now here I'm just initializing those weights and biases to the values that we have here on the diagram. Okay. So this cell is doing just that. And we can see that at this point, the gradients of the parameters are set to none because we haven't yet done any backpropagation. Okay, so if you do the same thing for the biases, weights, you'll see that all of them are set to none at this point. And note the syntax. So model.output actually refers to this. So we have a self.output attribute which stores that linear unit. And then if you try to access that, you can actually access the bias and the weights directly. Okay. So next thing, we define our loss function. All right. And then once I have defined my loss function, I can use that to compute the loss value. And here I've created the loss object, and then I can use it as a function. Okay, and then I pass y hat. This is how y hat is computed. You just pass x through the model, and then we have y's from the data set. Okay, and then just as we saw in the previous lecture, we do loss.backward. And what that backward does is exactly the process that I described to you. Okay, go from the loss to partial y hat to partial everything else. Okay, once we do that, then the values of the gradients of the loss function with respect to each weight and the bias will be stored inside of the .grad feature. If we do that, you can see that this time we have some values for the gradients. Okay, and you can see that partial L to partial B3, which is this value, it matches what we have computed on the diagram. 3.31 minus 3.31 over here. Okay, and then we can also check out other values, and I don't have enough room to show you the diagram and the values here, but if you do a quick check, you'll see that these values are essentially what you see over here. So the computations check out. Okay, so at this point, we have just computed the gradients, and we haven't yet touched the weights or the biases. So meaning that we have computed the derivatives, we haven't updated them yet. This is why we see those initial values inside of the model.state dictionary, hidden weight, hidden bias, output weight, output bias, they all still set to the initial values. So in the next step, we have to define our optimizer. In this case, I'm using stochastic gradient descent. And by passing the parameters of the model to it, it knows where to obtain those gradients from. And then once the algorithm has the gradients, it can do one step of the gradient descent. So when we do that and then do optimizer that step, it goes and grabs those gradients and use them to make one step in the optimization procedure. Okay, this time if I do this, you can see that if you compare it, these are just all whole numbers, and then here, according to the gradients, those weights and biases have been updated. Okay. So one thing to note that also came up in the last lecture is that PyTorch does not clear the gradients automatically. So here, for example, I'm clearing the gradients at the first step here, but then I create a loop and then repetitively do loss.backward. If I do that, you can see that the value of the gradients is accumulating. So at each step that I do that, it computes the gradients and it adds it to the values that I currently have in the .grad attribute. So we have to be careful about that. And we have to manually do optimizer.0_grad in order to clear the gradients at each step. You can see that if I do this optimizer 0 gradient and then repetitively compute the gradients never change because this time I have zeroed out the gradient values. Okay, so The reason that PyTorch behaves like this and it doesn't clear the gradients, there are two notable reasons. One is that sometimes we are interested in using larger batch sizes, but because of hardware limitations, we're not able to do so. So one thing that you can do, because the loss function is a summation over the data set values, you can compute the loss function over smaller batches and then let the gradients stay there, compute the gradient, let the gradients stay there, and then compute the gradients using other batches and add the gradient to the existing values, and only then update the weights. So because the gradient of the loss function itself has an accumulating nature, because it's a summation, you can imitate using a larger batch by just accumulating gradients, not update the weights, wait until the end, and then do one update of the weights. So this is one thing. The other thing is that if we have multiple loss functions, which happens in a lot of cases, more complex networks, then this is something that we prefer. We want to accumulate the gradients, and then we don't want to update the weights before computing the entire gradient. So we have to wait until the gradient with respect to each of those terms is computed and added up, and only then we can say, okay, this is the gradient of my overall loss function. So in that case, again, this accumulation helps us do that without saving intermediate results anywhere, because that could be problematic. Okay. So in the backpropagation algorithm, just like I showed you, we compute the gradients of the loss function with respect to each weight and bias, and then we go stage by stage. And okay, what happens if I don't save intermediate results anywhere? So suppose that I want to compute the gradient of the loss with respect to one of the weights all the way at the back, closer to the inputs, and then do everything else in between. When I want to do this, basically, if I show that to you on the graph, suppose that I do something like this. Okay, suppose that I want to compute the gradient of the loss function with respect to B2. If I haven't already saved the intermediate results of computing the gradient of the loss function with respect to W4, with respect to A1, A2, then each time that I want to compute the gradient of the loss with respect to any of the other parameters, I have to do all of the computations along the way, again and again and again and again. So there are a lot of intermediate computations that I have to repeat over and over again. Again, this is similar to something we have seen in 512. And if you remember from recursive algorithms, the running time was exponential. However, there was one concept. And if we use that concept, then the running time is no longer exponential. What was the, pardon me? Yes, exactly. So memorization or caching. So basically what we did is we defined a dictionary and saved intermediate results. And instead of doing the computations again, we just go and retrieve that result. So essentially, in the backpropagation algorithm, the same thing is done. So we create a graph, and on the graph, we store those intermediate results, and then whenever we want to compute the gradients, we don't recompute everything, because if we do that, we have lost a lot of efficiency. What's the downside of doing this?
It's very costly in terms of storage, and in particular with learning, I'm assuming there's
Exactly. It's in terms of space complexity, we incur a lot of costs, and that's why the memory requirements for training large neural networks is much higher than making inference or predictions. That's because you have to create a huge graph structure to store your intermediate results. Okay, so let's take a break, 2-3 minutes, and we'll be back at 11:15. Okay, we are back. So, thanks very much. Thank you. Okay, so the question about this derivative, the derivative of a2 with respect to z2, yeah, it's a little bit to see right away by trying to do the derivative without writing it down. So this is the format. Basically what they do, I forgot about this. So what they do is that they take the derivative in the usual way, and then they use the function itself to redefine the derivative in this form. So just like any exponential function, when you take the derivative, you can redefine the derivative in terms of the actual function itself. You can do it in the same way here. So that's why what we had here was a2 multiplied by 1 minus a2. That's actually the derivative of the sigmoid function expressed in terms of itself, rather than expressing in terms of just exponential, as you can see over here. Okay. All right. Okay, computational graph. Let me also show you this blog post over here, which I think is going to be interesting. So you can check out this link if you want it. Basically, the graph looks something like this when PyTorch works under the hood. So we have the variables, then we have multiple predefined operators in PyTorch for which the derivatives are defined, so we know everything about them. And as you can see here, for example, log of x multiplied by y is decomposed into these more primitive elementary operations: a multiplication, then a multiplication, then taking the log of the result. And in more complex cases, essentially the process is the same. Okay, so you can see that at each point we know the derivative of those basic primitive operations, and that's what we use when we do the back propagation. And when you do more complex cases, let me show you this at the bottom. Okay, for example, here we do the forward pass x1, x2, multiply them, pass them through the log, and then add something else to it, like sine of x, and then do something else. So a lot of operations along the way, but it doesn't matter because we have a mechanical algorithm in order to compute the results. For each step, we know the derivative of the function, and once we do the forward pass, we have computed the function values, and when we go back in the backward propagation, we simply use those derivatives and multiply things together in the way back. Okay, just a visualization. Okay. Again, this is similar to the concept of caching or memoization. Not entirely similar in the sense that we save intermediate results on a data structure in order to avoid recomputing the intermediate values. All right. So, one potential problem with the backpropagation algorithm is what's called the vanishing or exploding gradients problem. So, when you compute the gradients, you can see that as you get closer and closer to the input stage, you can see a larger number of terms multiplied with each other. So that means that if you have numbers smaller than 1, then your gradients keep getting smaller and smaller and smaller. And if your network is deep enough, then you might run into the problems of underflow, for example, along the way. And as soon as something like that happens, then the neurons at that stage are called to be dead, because you cannot update them with the backpropagation algorithm anymore. So that's called the vanishing gradient problem. And the vanishing gradient problem is especially a problem in neural networks trained with sigmoid functions. And the reason is, with the sigmoid activation function, if you plot the derivative, you'll see something like this. So that's the sigmoid. However, you can see that the derivative goes to 0 when the function saturates on both ends. So it means that if your inputs to the layer, your inputs to the sigmoid function coming from a neuron are way in the positive range or in the negative range, then your derivatives are very small, and this is going to get worse as you go back through the network. And this is why the sigmoid activation function is a particularly bad choice for training deep neural networks. For 1 hidden layer, 2 hidden layers, 10 hidden layers, might not matter that much, it depends. But if you have deeper networks, then this is a huge problem. Okay, so what people have done is they have stumbled upon other activation functions, and I'm purposefully using this term "stumble upon" because a lot of what goes on in neural networks research and deep learning has been based on empirical evidence rather than rigorous derivations or findings. So if I show you these activation functions, for example, we have sigmoid, we have the hyperbolic tangent, again suffering from the same problem. However, researchers have found that if we use this particular activation function called rectified linear unit, which is 0 for anything smaller than 0, and basically x, or identity function, for anything greater than x, then this has been shown to effectively eliminate the problem of vanishing gradients, or improve the situation a lot. And that's because you can see no matter how large your value is, your input is, the gradient never vanishes. And for you'll see that especially when we do image recognition, our networks are relatively deep networks. We will almost all the time use the ReLU activation function. Another thing, okay, you might say, okay, this is in the negative range. This is suffering from the same problem, that the derivative becomes 0. There's a variant of ReLU called leaky ReLU, which basically leaks in the negative range with a very small slope, so that in the negative range your neurons don't die and they have a chance to get updated. So that's the reason behind using ReLU and leaky ReLU in the codes that we have seen or you have seen in the lab or in the lectures. A similar problem is the problem of exploding gradients, which again is the same thing. If your values are larger than 1, then multiplying a lot of those terms together can result in gradients exploding. Sometimes this, together with a bad initialization or a bad starting point, can give rise to exploding gradients, and you'll end up in overflow errors. Your network, your convergence just oscillates a lot around minimum values, and you're basically unable to train. So there are various strategies to prevent these from happening. They're not ultimate solutions or cures, but they usually help a lot. So I've talked about the ReLU activation. For exploding gradients, one thing that we can do is gradient clipping. So if the gradient values are larger than a certain value, we can limit them to a range that we like. That's usually very effective. We can use different weight initializations. That usually helps. For training a lot of models, people usually explore a lot of possibilities for weight initializations to see if they get better results. Other things, you can change the network architecture. Particular architectures might be more or less prone to vanishing or exploding gradients. You can play with the learning grades. That might not be so effective, but sometimes it helps. Two very interesting approaches are also noted here. One is batch normalization. So with the sigmoid function, if we can do something at each layer so that we limit the inputs, for example, between -2 and 2, then potentially we can alleviate this problem of vanishing gradients, right? If we make sure that our inputs are always, for example, between -1 and 1. This process of renormalization of the inputs is called batch normalization, and it's done in each layer. I will show you how effective it is in larger networks in the next lectures. But this is one way to deal with this problem. The other thing, a very, very interesting approach, is using an architecture called residual networks. So a residual network is a very deep neural network in which we have highways of information. So instead of making all information sequentially pass through the layers, we pass information through the layers, but then we create skip connections. So we pass for example, the inputs to the first layer, not only to the first layer, but also to the 10th layer, and then from the 10th layer to the 15th layer, something like that. So skip connections, or they transfer or they communicate the residuals to the later stages of the network, and they are very effective. So there is a very famous architecture called ResNet 50, ResNet 100. There are different variants for image recognition that are very, very good. And I'll show you how they're built, how we can train them in using PyTorch. All right. Okay, questions about vanishing exploding gradients? Yes?
I might be missing something here, but I'm trying to understand if sigmoid function is always going to change from 0 to 1. I can understand the vanishing gradients occurring, but how does the exploding gradients occur? Like sigmoid function is multiplied with something else, which leads to a value greater than 1.
Oh, okay. Yeah, sure. So it's for situations when we don't use sigmoid function. For example, these other, ReLU, for example, is a very good example of a way to prevent that, but then you're susceptible to exploding gradients, for example, because the value of the gradient is always 1 for the activation function, for example. Yeah.
I'm wondering how ReLU introduces non-linearity to the model, because if it's just an identity, when it's greater than 0, what is that?
Yeah. So how is it that the ReLU activation function can inject that nonlinearity into the model that we want? So basically what I discussed this a little bit in the video, that for the activation function, it seems like the details are not that important. What really matters is that your activation function gives you a transition between two states. That's the only. So with ReLU, it gives you a state of 0 and a state of 1. That's basically what matters. It seems like it doesn't matter if the function is continuous or anything. And you can actually use functions that fluctuate a lot or very complex, but they give you a transition. You can use any of them in order to train your neural networks. It doesn't matter. As long as you can create a transition or a step between two states, they work just fine.
It seems that the ReLU will vanish for the derivative half of the time once you get below 0, but it seems that in our labs the ReLU works very well. Is there some techniques that it uses to prevent this vanishing? Because we didn't use leaky ReLU, so how does this work?
Yeah, so this is why the leaky ReLU has been invented. But the thing is, if you use ReLU, the network learns to shift the inputs to each layer to the effectively to the positive range, and then by playing with the weight and bias, then you can play with the location of that transition, and you can work out the function approximation in that way. It's hard to really imagine that, but basically it's not that much different from the sigmoid. So the sigmoid eventually also dies out. It's just the fact that it dies out discontinuously and very quickly. That's the only difference. Yeah. Okay. So let's move on to the next section, and let me see. Okay, we have covered everything here. Okay, so here I have a trainer function similar to what we had in the previous lecture, and I told you that the important part is that here in the trainer loop, we have these few lines that basically do the most important parts of the model training. And can you tell me which parts here correspond to a forward pass? I know there's a comment there, but there's a little bit more to it. So the forward pass is actually both of these two steps, not just the top one. because the end result of a forward pass is computing a loss value. So these two lines of the code are the parts which do the forward pass. And then this is the back propagation, and finally using the gradients to make an update to the gradients. And the rest of this is not too important. This is just keeping track of the losses so that we can look at them, plot them, stuff like that. Okay, let's run this. And then this is just a toy problem, x and y. Y is the output, x is the input. And then here I'm defining a network that has 3 neurons in the hidden layer. And the usual stuff, we define the criterion or the loss, and then we pass the model parameters to it, we specify the learning rate, and then finally we run the trainer. And then if we look at the results, this is the results of fitting a neural network to this data. Now, I'll use this to show you the convergence history. So this is the results of the loss function, the values of the loss function, as a function of the number of epochs. So you can see that the loss drops very quickly to small values, and then it kind of starts to decay to a change of 0, basically. Loss plots are very, very helpful in seeing the progress of your models, and I suggest that you do this in the labs or whenever you do train neural networks. This is really helpful to see what's going on and how your convergence is going, how your optimization is going. Especially one thing that's really important to look at is the plot of training loss and validation loss, because potentially that can tell us whether our model is learning or it's just overfitting the data. So let's take a look at that. Here I have modified the code a little bit to not only look at the training loss, but also the validation loss. And there's a little bit of, just a tiny bit of detail here. The training loop is very similar, just the same as before. I keep track of the losses. However, in the validation loop, in the validation loop here, over here, we're not doing any backward step. We don't do back propagation, because the purpose here is just to assess or evaluate whether the model is doing a good job. So what we do is that we have a train test split or train validation split, and in the validation loop, what we do is that we pass the X of validations to the model to generate outputs, and then we apply the loss on that to compute the validation loss and keep track of that as well. However, the important thing here is this bit, one of the important things. So with torch.nograd, it means that we're telling PyTorch, hey PyTorch, stop tracking the computations and stop building the computational graph. Because here I'm just trying to, I'm not trying to do back propagation. I'm just trying to test the model. So this is what it's doing. Okay, torch.nograd. And then if we do this and train the model again, this time we see something like this. So you can see that until 50 epochs we're doing good. Beyond that, the validation loss is starting to increase. So we are starting to overfit. Okay. One thing that we can do, one strategy that we can use is to implement an early stopping condition in our training loop, so that if we see that, for example, the validation loss is increasing for a number of consecutive epochs, then you just stop the training so as to not have an overfitted model, basically. So this is why you, in most codes developed by other people, you see this early stopping thing. And the code for early stopping is just very simple. You just keep track of the validation loss, and then whenever the validation loss becomes greater for a number of consecutive epochs, you just stop the training loop. That's basically it. And we call that parameter the patience of the model training. If we do that, run this again, you can see that it says, okay, stopped early at epoch 53, val loss increased for 3 consecutive epochs, and that number 3 is something that we have set in the trainer function. We say that we have patience for 3 epochs, but nothing more than that. Because sometimes the fluctuations, stochastic gradient descent, the loss value may increase. That's okay. But if it's consistently increasing, it means that we are overfitting. Okay, so you can see that here, the process has been stopped before the model overfits. Okay, questions about this? Okay. So with neural networks, we can regularize our models so as to prevent complexity, basically. There are various ways to reduce complexity of the model, reduce unnecessary complexity of the model. One of them, you are already familiar with it, L2 regularization, which forces or makes the unnecessary weights smaller and smaller. And the other one is the dropout technique. With L2 regularization, it's very simple. It's just the parameter that you pass to the optimizer. There's not much detail about that, or we don't talk about that very much. But dropout is something specific to neural networks. So with dropout, we try to prevent some neurons from specializing to certain parts of the data set. And it has proven to be very effective in preventing overfitting. So what we do is that in each iteration, we randomly turn off some of the neurons. And we make the training process, we make the neural network to use other neurons in the network in order to optimize the loss function. So we do this randomly in each batch, in each epoch, randomly turn off a bunch of the neurons with a certain ratio, and then that helps avoid or prevent specialization of some of the neurons to memorize basically some parts of the data set. Okay, so a dropout can be defined within PyTorch as a layer. So just like we have a hidden layer, we have an activation layer, we can also have a dropout layer. And it accepts a parameter called P, which is the probability of neurons vanishing or going to 0. For example, here I'm defining a tensor of random values. And if you take this dropout layer and apply it on these random values, what you'll get is that you can see that with a probability of 50%, the neurons, the values are set to 0. Yes? So that's something that we have to decide, whether we want to have a dropout at each layer or some of the layers. That's something that we have to decide. If we go too aggressive with dropout layers, then it hinders the training process itself. So we have to use it in moderation. Yeah. Okay. So I'll show you an example of how this is used in a neural network later on. With, just like I said, with L2 regularization, what we have is a parameter here in the optimizer. It's called weight decay. And the parameter that you specify is the value of lambda. Okay, this is just as much as we discuss here because there's a lot of other discussion that is attached to it. I don't want to get into that. Okay, something that I want to, before going to the lecture exercise, something that I want to stress is the concept of regularization is, despite what I have just discussed, dropout L2 regularization and that's it, it's actually conceptually a huge topic because regularization allows us to decrease unnecessary complexity of a model. And most effective regularization techniques actually come down to structural regularization or structural bias. So although neural networks are very powerful, they can fit complex data very well. However, it's not guaranteed that we can find a good structure for our neural network or a good result from our training process if we just stack layers upon layers and try to fit complex data. Sometimes we have to purposefully design the structure of the network based on the domain knowledge, based on the information about the structure of the data sets or or where the data set is coming from, and then try to guide the neural network to learn the proper representation. So it's not like a hammer that you use for everything. You just apply a raw power. It doesn't work that way. We have to guide the neural network, and we have to give it usually structural bias or structural regularization in order for the model in order to prevent the model from over-complexifying and overfitting the data. I will discuss this much more in the next lectures. This is just a kind of an intro to that concept. Okay, so as lecture exercise, for this one you have to do git pull. I have updated the Bitmoji data set, so you can get rid of the data.zip file that you have on the repo. You don't need that anymore. I have changed things and moved things around. So what we do here is that I have a data set of Bitmojis, and some of them are my Bitmojis, and some of them are other people's Bitmojis. And I want to create or train a classification neural network in order to classify, do a binary classification to detect whether a Bitmoji is mine or if it's someone else's. Okay, so this is the directory. You have to take the Bitmoji RGB. Okay, this is for the lab. So you have to copy the folder for the lab, but for the lecture, you just do git pull, and the data set is here inside the data folder. And I'm doing a number of things here, which I'm going to explain right now. So I'm going to explain these steps in the later lectures when we do image recognition more in detail, but just for you to know, PyTorch has some convenience functions to do transformations on the data set. For example, something that we have seen in the previous lectures is that we have to take the data set and convert it to PyTorch tensors. We can't do that manually, but PyTorch gives us some convenient ways of doing that. If we want to do a bunch of such little steps, we don't need to do it every time ourselves. For example, here, because I have images, I might be interested in resizing my images and then maybe converting the image color map to something else, and also then converting all of those values to tensor values, PyTorch tensors. We can wrap all of those steps inside of a transforms.compose function, and then this passes the data through these stages and does those transformations to the data set before training a neural network. So this step this is what it does, but I'm going to discuss this more in detail in the later lectures. We also have another convenience function called image folder. So if you have a folder that contains images for your neural network, instead of having to import the images and manually create labels for them, if you just put different classes into different folders, PyTorch automatically imports that for you and assigns correct labels to them. So this is, again, something that makes our job much easier. And then the rest of it is just the data loaders, which create the batches for us here. These are the data for, and then this is just for importing the images into our runtime. In order to see a sample of a batch, these are the Bitmojis. We're using grayscale at this point because we haven't yet learned about more complex ways of doing this. So this is just a simple, fully connected neural network that we're going to train. This is a batch of data. You can see my Bitmojis along with others' Bitmojis. Okay, so here, for the classifier, what I do is that instead of repeating things in my model, I define a function that creates a linear unit, a leaky ReLU activation, and a dropout. Put them inside a function to simplify things. And then here, I basically just create a bunch of these linear blocks. So for the first step, I use the input size of the image, whatever it is. And then, to decide how many neurons I can have in the later steps, I can use whatever values I like. This is just something that I have seen that it can basically work. And in the last layer, I compress all of that information down to one output value. And if you have watched the Lecture 4's complimentary video, you know that for a classification problem, instead of applying sigmoid in the model structure, I don't do it. I use a different loss function called a binary cross entropy with logits for numerical stability. So these are just unnormalized score values instead of probabilities. And if I run that, and this is kind of similar training loop, and again, similar stuff here, defining the model, defining the loss function, and optimizer, and then do the training. So this is the training procedure. Okay, train accuracy, valid accuracy, you can see 5250. It's a random in the beginning. Then it starts learning some stuff. You can see validation accuracy over here starting to increase, getting better and better. Okay, 63% on the validation, and on the training 668. Okay, it fluctuates a little bit. Okay. All right, we stop there, and you can see that this is what we get. So this is the loss values, and this is accuracy. You can see that the training loss is starting to kind of overfit before modeling the data properly. So this model is not so good, and the reason is that you probably can't get much better results if you play with the number of hidden layers and stuff like that. And this was a problem a while ago. People didn't know how to do image recognition efficiently. This is the accuracy that you get, 60, 70% maximum. And this is where other architectures for neural networks come into play, which regularize and guide the model into learning the right patterns. So one thing that I wanted to point to is the universal approximation theorem. So before we end this lecture, there is a family of theorems called universal approximation theorems. One is for neural networks that states that any continuous function can be approximated arbitrarily well by a neural network that has one hidden layer with a finite number of weights. So basically, any function that you have, as long as it's continuous, you can approximate it with a neural network. The catch is, it doesn't tell you how. So this is an existence type of theorem. It says that something exists there. It's guaranteed that there is a function, a neural network that can approximate your function. But it doesn't tell you how to obtain that function. This is where we have to start flexing our neural network deep learning muscles and start using more specialized architectures for our deep learning models to be adapted to image recognition, voice recognition, time series data, video recognition, stuff like that. This is the topic of our next few lectures. All right, are there any questions? Yes?
So the loss and accuracy, are they on the same scale?
No, they don't have to be. Because yeah, no, they don't. They absolutely don't have to be on the same scales. No. These are completely independent. Yeah. Any other questions? All right. Thanks, everybody. See you in